questions on that program thing, the simulation? It's due today. One person asked to have it extended to Wednesday, but so it's okay. Need more time with it or something, but doesn't matter that much. I'm way behind on grading the thing. So anyway, so today I wanted to go through do some stuff on polymer membranes because some people are working in that area. And then I'm definitely not an expert in that. So just thought I'd try to go through some things on it. There's some papers here on membranes on the web page. They're kind of piled in here. So it's like there's the slides, and then there's a review on membranes. Everyone has like a different approach. So if you kind of like this review's pretty math heavy, and then there's different kinds of membranes, like different fields. So people, anyway, you can kind of look through those if you want. Then there's a book in here on membranes. It's pretty good. I mean, it's kind of comprehensive, but it also has its own track on the thing. So just search membranes. It's down at the bottom somewhere. Here, not that one. Not this. Where is it? Oh, not membranes, it's a membrane. That's what we here. Membrane technology. So I mean it's kind of an old book, but it's I think it's like 2019 or something. I don't know. I'm not sure how old it is. Anyway, you might want to, if you're interested in membranes, this is pretty good from a kind of physical chemistry perspective. It goes through every kind of membrane. So it's not a bad thing to look at. What year is this thing? I think it's like 2019. So it's a little bit old, but anyway, so I just wanted to kind of go through a little bit on membranes. That's all. But that book's kind of a good source if you want to do that. And then, so I think what I'm going to do is just take this. We have this paper by Sanat Kumar on nano particle composite membranes. This thing, so somewhere in here. Nature paper, like this paper. So I thought that, so the final is going to be 2 papers. So I thought I'd take that paper and then take another paper that I haven't figured out what it is yet. So, which will be like something more on a different subject, you know. So then anyway, so I thought maybe like today I could go through the membrane slides, which is 109, but they're mostly just pictures. So I think we can flip through that kind of. And then on Wednesday, maybe go through that Sanat Kumar paper, and maybe if there's time, go through some other things. Because so it's kind of more narrow focus, you know. So, and then on Friday, go through the other paper that I haven't found yet, like what that'll be on the final. So like 2 papers on the final. So then, and then maybe I can just summarize or something on Friday too. So it's kind of like 2 papers this week. And then just whatever I can do on membranes today, you know, if that's all right. Anyways, that's kind of the deal. Let's see. So let me just get this guy going. So there's this kind of different areas in membranes, totally different from batteries to cleaning up beer, like cleaning out the haze in beer, to sewage treatment, to making milk, like filtering out whey and things. So every industry kind of has membranes in it, and it seems like they'd be completely different subjects, you know, but they aren't. So it's kind of like they're, in fact, there's a kind of a field of membranes within chemical engineering They try to like unify all these things, polymer membranes, and somewhat even like ceramic membranes. So that even though they're like different subjects and they seem to be like so different, they end up being kind of the same from the perspective of people that want to have like membrane science as a field, you know. So that's kind of where it is. And it's a super applied field. So it's not like the first people doing membranes, doing polymer membranes was like if you read about it, is this let me see, sorry. What's the name of the two guys? The two guys at UCLA that were just playing around with cellulose acetate just to get salt out of seawater. Those guys' names. Oh, well, maybe it's pretty far deep in here. Their names here, no. I'll have to find it again. But anyway, if you read about it, they're just first they take a sheet of cellulose acetate and just kind of pump seawater through it. And it kind of works. Like they can get us 1 ml of it or something after pumping for a week. Right. And then they basically find out some things about how to make porous membranes and like how you make thin film membranes on top of porous substrates. Anyway, in the end, they're able to like distill seawater using reverse osmosis after like 20 years or something, right? So basically it's all just applied, like try this, try that. So it isn't necessarily like based on such a scientific approach. So it's really totally like an applied field in a sense. But in the other sense, it all depends on molecular diffusion. So people like simulating membranes. And then since there's a lot of money in it, it's basically attracted different people. Like Sanat Kumar's going doing membranes. Like why would he do that? Right? Because he's kind of more fundamental. So anyway, so it's basically there's industrial importance to it. So people just do it. So anyway, within the polymer area, you can kind of look at so porous membranes. So if you're like on the micron scale, so human hair is 50 microns. It's like human hair thickness pores in a material. So you can do that by a variety of ways, and you can do it by phase separation. So typically polymer phase separation is going to be on a 50 micron range thing. And then there's different kinds of phase separation. You can do it by thermal phase separation. So you have something that's miscible at a certain temperature, and then you drop the temperature and it phase separates. And then you can somehow wash out one of the phases and end up with a porous membrane. You can do it by taking a plastic film and blasting it with ions to get smaller pores. You can do it by taking a polymer in a solvent and then dumping it into a non-solvent. So that's like a really popular method. And that's what these guys in California ended up doing, was like to make this reverse osmosis membrane, was to do this non-solvent induced phase separation membranes. So that's an industrial process. And later, so this is in the end of World War II, like 1949, 50, and then into the 60s, and this Millipore company was getting money and grew into like the biggest company in the business for doing that. And they have a facility in Norwood. They don't do membranes there. They make they distill I think they distill solvents or something. For anybody work at Millipore? Anyway, there's co-op jobs there for the undergrads. So anyway, when you go on the Norwood lateral, then 71's coming down, and there's a bunch of distillation columns. So the two companies share that site. Millipore distilling solvents, and then Shepherd Catalyst Company. Shepherd Color and Shepherd something else. They're like a Cincinnati chemical company, small, kind of marginal, medium scale company. But anyway, so Millipore is in town. I mean, so mostly I think they're based in Boston, and their origin. So they've been around since World War II. So it's, I guess, 80 years or something now, right? Something like that. So anyway, and they make all different kinds of membranes, right? So if you want to do microfiltration on that scale, you can do it just by using a non-woven like polypropylene. So you can just take, you can just spin polypropylene fibers, so extrude it, then blast it out onto a conveyor belt that's flying by and just let it raster all over the place and end up with like a mat, like a dense mat of polypropylene fiber. And it can make pores on that size scale. So that's like the cheapest way you could possibly do it. Another way is you could take polypropylene film that's semi-crystalline and then like stretch it, and it rips holes into the material. And if you do it in the right way, then you get pores like that. So this kind of large scale porous films, there's a variety of ways to get it. Right. So then as you get smaller, it gets harder, right? As you try to make nanopores, then you're gonna have to make gonna have to kind of use some techniques that are different than that. Right. So I mean, another thing that the guys in California found out in the 50s was that if you take something like a mat, like a non-woven mat, and then you change the temperature, if the pores are small enough, you can change the pore size using the temperature. So they found out that they could get bad separation of salt and water at room temperature, but they heat it to 80 degrees, all of a sudden it would work great. Right. So they found out that like thermal expansion and in fact thermal contraction, because in polymers you have this rubber elasticity issue. So it's like the modulus goes with Kp over the molecular weight. So if you raise T, the modulus and kind of the modular response to force increases, so that actually the pores shrink when you heat it because it's tensile pulling it together, right? So it's basically all these things were found by accident in the membrane field, and they just said they adopted it empirically to make the membranes, but they're based kind of in physics. So later on, people pieced the things together. There's like a physical process that's going on. It's kind of like retrospective of an empirical field, a lot of ways, So one thing is that if usually you're gonna put a pressure across the film. So you're gonna have a film, put a pressure across it, and the pressure drives the separation, say gas separation. Or you're gonna have a concentration gradient and try to drive the separation with a concentration gradient, right? So generally with pressure, you're worried about the film breaking, like it can rupture, right? There's two things you're worried about. The film, so if you're kind of doing microfiltration of, say, clarifying beer, so basically the beer goo is going to get stuck on the membrane, and then you have to have a way to flush it back out. So that means you got to change the membranes all the time, or have a process where you're like running the fluid through it, and then once in a while make it back flush and clean it out. Like in the environmental field for wastewater treatment, the back flushing routine is pretty typical. And in industrial microfiltration, replacing the filter is kind of more typical, right? So that depending on what you're doing and how expensive your filters are, you might choose one of those two ways to do it. So that kind of clogging of the filters is a problem, and rupturing of the filter is kind of the other problem. So if you're dealing with pressure, the idea of pressure is that it's force per area is pressure, right? So if you can reduce the area, you can reduce the force, and the force is actually what ruptures the film, right? So if you can make your membranes really small, like your separation membrane small, then you get less force on them, so they can withstand higher pressure. So basically everything you're thinking about doing, so that when you first go into the lab and say, I'm going to make a separation membrane, you take a sheet of plastic saran wrap and put it on a big thing like that. And then that's the worst thing you could do, because the force on that saran wrap is going to be huge, because it's the pressure times the area, and you have a big pressure and just blows out and blasts through. So if you can make it into a tiny fiber and somehow wrap it up so everything is really small, but you have a large scale flux through it. So the whole idea of this is try to whenever you're dealing with pressure, you want to try to get it down into small things so that the force is smaller, so it doesn't blow up the system. So all the tubes, like if you're doing 50 megapascal, all the tubes going to be 1/8 of an inch, because you want to have like really small tubes, so it's a small force, even though you have a huge pressure, right? So that's generally like the rule of thumb here, is you're going to try to design it. So again, it's like engineering, just how to design it so that you have really small fibrous membranes that again, or rolled films, so you can have everything really tiny, right? So that you can withstand high pressures. The high pressures can drive whatever you want to do, either microfiltration. So so depending on what range you're in here of size of the pores, there's different kinds of separation that are going to go on. So large scale things, and then the pores. In this range, you're starting to get into what they call Knudsen transport. So that's when if you're looking at kinetic theory of gases, the gases have a mean free path. And if you get a pore smaller than the mean free path, the transport's not governed by gas molecules hitting each other, and then you get Brownian motions, you get diffusion. It's guided by the gas molecules hitting the walls of the pore. And they don't see the other gas atoms because of the size of the pore is so small, it basically acts like a dilute gas at that point. But the pore drag. So anyway, the transport drops, but the dependence of the transport on the size of the pores changes dramatically when you go from diffusion to this kind of Knudsen transport, right? So basically, the idea of like microfiltration, ultrafiltration, you get into this region where the gas or ion or whatever kind of thing is being separated, the transport regime changes from a continuum to this molecular scale transport. Right, so that changes the properties of the behavior of the membranes. So there's those are all more or less porous membranes, and then there's dense membranes, which would be just a film. So this is like reverse osmosis, where you're doing like molecular scale or atomic scale separation, right? So basically, the dense membranes aren't going to be dense membranes. They're going to be something like this. So you're going to have a porous membrane. Could be a different material or the same material. So there's ways to do this with the same or different material. There's going to be a solid film on the other end, right? So there's kind of like rapid transport through this part. Then all of a sudden you get to the slow transport through the film, and that's your separation layer. So you want to have a good. So this whole thing is like around this idea of this resistance model for which is in here somewhere. For transport through a membrane. So this kind of idea, like you have that kind of structure, and then you have rapid transport for the bulk of it, and then you have a separation layer. It's as thin as you can get, right? Because the flux is going to be, the flux through the membrane is going to be inverse to the thickness. The thicker it is, the lower the flux. You get the thickness to 10 micron or less than 1 micron, and all of a sudden your flux can go high even for something that wouldn't have much flux through it. So people have develop this like electric circuit models for flux through this thing. Like you could say there's like a parallel resistors in this part. This is like the most simple of these models, because you can do all kinds of treatments to these films. You can talk about capacitance in these models. So they add in the entire gamut of electric circuit. They don't do AC. The DC electric circuits. The entire thing is in these kind of models for transport through these. So I'm just showing this picture to kind of show how that would work. Like this would be a parallel resistor, which would be like the 1 over the harmonic average, and then this is a series that's a numeric average. So you do harmonic numeric equation to get the total resistance through it. All right, so even in composites, they use like this kind of electric circuit analogy to do the math for how a composite would act, but anyway, so that's kind of this resistance model membrane thing. There's a paper on a web page that goes through that. That's not in that book as far as I could see. So anyway, so we got that business. These are some of the polymers, because you're going to have like stress on the thing, you end up with, you want to have really strong polymers, and sometimes depending on what you want to separate, so the polarity of the side groups matters. So this is polysulfone. It's anything that's got aromatics in the main ring, kind of like stiff polymers that are going to have high modulus. So you want high modulus in this. You want good tear strength. So you're going to find like all the high strength polymer is going to be used in this, like cellulose, relatively strong polymer, and then cellulose nitrate and cellulose acetate are like the two kind of osmosis membrane things. Basically the polarity. So they're hydrophilic for water separation, osmosis, hydrophilic, and basically also tough. So So basically, they're hydrophilic because when you have a membrane and you're doing, and it's a solid membrane, the porous membranes, you worry about wetting the pores. So you want to have either hydrophilic or hydrophobic if you want to have the pores wet by the thing that's flowing through it. And that brings up another issue that, so there's a lot of issues in this whole field about like how you model the transport through a membrane. One is going to be, well, you have a pore of a diameter 5 angstrom or 10 angstrom. And then you're going to have like water, if it's hydrophilic, the water hydrogen bonds to the surface. And that means the pore is actually smaller than that because it's got stuck water to the surface. The thing's transporting through the middle. So you can see this whole thing, and depending on exactly what you're working on, all the models of it will be different. There's not necessarily like a generalized view of it. Everything becomes very specific, but they do like bring in a lot of different topics into this, right? So anyway, so hydrophilic is good in the case if you want if you have a solid, so that's a porous membrane. If you have a solid membrane, then you have to worry about, does the stuff dissolve in the membrane? If you have a membrane and it's like saran wrap and it's hydrophobic, it's not going to transport water, right? Because the water can't absorb into it, even though water might have a huge diffusion coefficient inside the film. Once it gets in, if it can't get in, then it's not going to transport. So it needs to like open the door and get into it, and then it has to walk across it. The two things, so the permeability of the membrane is going to be a combination of the solubility and the diffusion coefficient. I mean, multiplied. As the diffusion coefficient times the solubility gives the permeability. So you need the two things together. If you don't have, yeah.
What if you're trying to transport hydrophobic materials?
So if you have a porous, it depends if you have a porous membrane or a solid membrane, right? So if it's porous, it might not matter. You might not want it to be oleophilic, right? Because basically that kind of slows down, it closes the pores in the porous membrane. But if it's a solid membrane, then you want it to be totally as much soluble as you can get, right? So it's kind of like it's a trade-off depending on, and usually the membrane is going to be a mixture of the two if you make it from one material, right? So you're going to have pores, and then you're going to have a solid film that's going to do the separation for you usually, unless you're just filtering out goo, like for cheese industry or whatever, right? So basically, what was the question for? Yeah, this oleophilic materials, polymers that you can use for separating hydrophobic things. I mean,
so the solubility of like material is dependent on the type of membranes.
Right, on the material you use. Yeah, so that's what materials. Yeah, and you can almost use a group contribution method, just figure out the del solubility parameter, find something that matches it. So there's tables of solubility parameters, a number, you can calculate like the chi parameter from it, right? Difference of the del squared gives you the chi parameter. So you can find two things with the same del will have a chi that's very low within the mix. So chemical groups, you can just do the groups in a polymer and see if they match up with the thing that you want to solubilize in it. So I mean, so basically that's generally how people do things. Yeah. Like in other words, if you're separating water, like say you're trying to do reverse osmosis and you want something that has this hydrophilic, like cellulose acetate, then the water can dissolve in that. And I couldn't hear you. Yeah, well, the polymer is the membrane, and then this thing you're separating can be a gas, can be a liquid. I think that's the two choices, a gas or a liquid. Right. So basically the things you're separating are just chemical engineering stuff. Like whatever junk someone wants to separate. Gases, like a lot of gas separations of, like if you want to separate ethylene from ethane in the petrochemical industry, to do that, it's not possible to do that by distillation. So yet the gas streams from natural gas, so they have different markets. So ethylene is going to be used to make polyethylene, ethane's is a chemical precursor, or you can burn it. Right, so, or you can put it through a process to dehydrogenate it to make ethylene from ethane. Right, so, but basically, in the chemical industry, you want to separate those two, and they're exactly the same molecular size, and they have the same hydrophobicity. So the only way to do it is with you can use membranes to do it, membrane separation. There's a slight difference in size, I guess, and there's a difference in polarizability. So you can select those. It's like a membrane that does that. So people are working on developing techniques to separate various gas streams. I mean, air is mostly nitrogen, and you want oxygen from it. But oxygen is more polar than nitrogen, so you could make a membrane that separates oxygen. It's like 21% oxygen and the rest is nitrogen, basically, and some other things. Right? So CO2, but basically not much. So if you're in a medical environment and you want to have oxygen, you can just get it from air, but you want it concentrated, or if you're welding or whatever, just use this for oxygen. So that's like Air Products does that, and they sometimes use membranes to do that. And it's always, membranes are always competing, like this pressure swing absorption process where you can separate oxygen from nitrogen and air too. So it's always competing against some other process, right? So basically membranes are one option, usually like the most expensive option, but in some cases the only option. Like for reverse osmosis of water, you can do things like just heat up the seawater and then just collect the condensate, and that's pure water. So you've separated salt water. The problem is, like, that doesn't exactly produce huge quantities to do that. You can set up systems where you have like solar driven distillation columns, separate seawater to make pure water. And that's been implemented in some places, but the vast majority of places use reverse osmosis. Even though it's kind of more expensive, you get the quantities out that you want. So basically, it's always compromise, like what technique you're going to use, and it's completely different infrastructure you need for the different processes too. So it's kind of like, anyway, this calculation's a cost benefit on this thing. It isn't exactly like this is the only answer, but anyway, so it is kind of a lucrative field to work in though. So anyway, so that's kind of, these are some examples of the things like cellulose acetates, the reverse osmosis for water, then acrylonitrile. You can see like the polarity of that group is going to be important to some separations. Vanillidine fluoride is a high strength polymer. It's used in batteries because it's got the polar groups. That's like a battery separation membrane type material. So you generally want to have thermal and physical stability. It's like kind of the things you want. And it's a lot of the same polymers are used for the different kinds of membranes. It's kind of basically all kind of strong polymers, some polar, some non-polar, to separate different materials. So yeah, that's kind of that business. This is just showing like you can look at this just as a list, or you can say like, what are you separating? So it's reverse osmosis, you're looking like salt and water you're separating. And then depending on, these are all biologically oriented, but basically conventional filtration and microfiltration are things like some kind of purification of a product. You're trying to get things like hair size stuff out of it. Right. So it could be strep virus, bacteria, whatever. And then there could be like filtering out, just clarifying things. Or this microfiltration is used for sewage water and also used for industrial wastewater separation. So the cost actually goes up as you go left too. The smaller size, the cost for the operation is going to be more. So the reverse osmosis process is the same as is the same thing as what we were talking about for measuring molecular weight, right? So you have, oops, here, get rid of this guy. Yeah. So basically, you have a membrane, cellulose acetate, and it's going to be a membrane like I showed you, where it's been made so it's got straight pores and then a thin film that's like a micron thick or less, right, of the cellulose acetate, and it's going to be wound into a canister, like a rolled film, and then you're going to pump in one side, and it's going to the film separates two channels, even though they're all tightly packed together, right? And it's going to just pump through, force it through. So it's going to do this operation. So normally, if you just let it sit with the cellulose acetate membrane here, if you have pure water and then you have salt water, so the pure water wants to dilute the salt water, so this will rise up, right? So under normal osmosis operation, you kind of remove the water and you've seen osmosis happen. So that's basically like if you're in the ocean and then the water drains out of your skin, so you get kind of like wrinkly skin. So this is actually not really a process. This is like what happens by accident if you get into a bath of salt water. You know? Then this is what happens if you to measure the molecular weight, like an analytic osmotic measurement. So the higher this goes up, usually this pressure is like nRT. So basically, you can get the number of salt particles that went in, and if you know the mass that you shoveled in, you can figure out the molecular weight of each one. If you know how many, you know the total mass you put in, then you get the molecular weight by the ratio. Right? So that's kind of an analytic technique. This is to make drinking water from seawater. So you have to put a pressure on it. You oppose this natural thing and like force the water to go through. You're kind of just using this as kind of a filter to drive this backwards. You know, this is just showing like basically how the pressure, water flux goes as you increase the pressure. Right? So zero pressure, you get this situation. You can match the two with a certain, when you match the osmotic pressure with the pressure on the side, you can get zero, same level, and then as pressure goes up, you get this separation going on, reverse osmosis. So let's see a cartoon of that thing. Let me go back. So anyway, yeah, so this is just showing that same thing, like pressure. So depending on the pressure, so if there's less pressure needed if you're just doing filtration, like through pores, the porous size separation process. And then you get to this reverse osmosis region. So this is the fraction of, say, salt that you can separate from the water. That increases as you get to higher pressure separations. So each would be a different membrane, right? It's not one membrane. And then at low pressure, you can't separate salt, but you can remove various molecular weight things. So as you go to lower pressure, you can separate higher molecular weight things. In other words, high molecular weight. In other words, if you're trying to separate haze from beer, it doesn't take that much pressure, and haze is large size. It's kind of what this is showing, right? So it's kind of a little bit of a useless plot, but well, this thing is really cooped up. That's why it's so. It's pretty disgusting. Years of goo things. So, I mean, this is just showing some structure. So the original membrane is isotropic, and the non-porous membrane is just a film. And then you can put ionic groups in. So if you want to do something like a electrostatic separation, so you can have. So if you have anionic groups, then this cations are soluble, and you can separate cations through this, so you put an electric field across it. Right, so you can have an anionic membrane or a cationic membranes to separate cations and anions and something like a battery. Right, so anyway, you can have electrically charged membranes, like you put chemical groups in that have either anionic or cationic charges. Then the anisotropic membranes, like the normal separation membranes, they have two sides. So if you, depending on how so these will have different separation properties if you run them forwards or backwards. In other words, they don't separate at all if you run them backwards. So you need to know which side you're looking at. And this is one of the first things that the UCLA guys figured out, was that they made a bunch of membranes, and some of them, half of them were like great and half of them were terrible. And it took them like 2 years to figure out that one side was rough, one side was smooth. That's what I mean by it's an empirical process. Literally took them 2 years to figure out. And then after that, they could produce perfect membranes all the time. You know, it's just like the major discovery. So they just show a cartoon, but it's like, you know, so anyway, so there's different kinds of structures. So the basic, I mean, if you have a porous membrane, then you're talking about tubes. I mean, this is actually tubes. You use Purcell's law to talk about the flux through it. If you want to talk about it in terms of, so you generally, they measure the porosity of the structure. So how much is holes? They have a porosity number. They want to know the number of pores in the material. That's going to be the porosity, the fraction porosity by the diameter squared. So the area footprint, if they're tubes. And then if you plug that in, basically you can get an equation for the flux through a porous membrane based on Purcell's law. Right? It gives you like the porosity, pressure gradient across this. This is a pressure-driven flow through a tube. And then kind of how many tubes is the porosity, and the diameter to the 4 ends up diameter squared because of the number ends up being like divided by diameter squared times the porosity. So basically that will give you the flux through a membrane. That's like the general equation people use to talk about. Oops, yeah. Yeah, yeah. I mean so the model is just that it's like a uniform. So the model is like this thing, except with straight pores through it. So that people will use that same equation to talk about this structure, like with no tubes in it. It's a tube equation, but basically the same, like, yeah.
I'm going to anisotropic number. Sorry, I'll interrupt your answer.
That's all right.
So because they have different properties on one side and the other, could you possibly do something where you have like some solution with like multiple components in it? You filter out one component on the way down and you filter it back, and then the original component that you filtered out, the first one, doesn't travel back, then filters out the second one on the way back up.
Yeah, you could do that. No one's done that.
No one's done that?
No.
Okay.
Yeah, you could do it.
You could do it, but nobody's done it.
Yeah.
Okay, cool.
Yeah. Yeah, yeah, you could write that as a proposal. But you'd have to find, I mean, it might be nice if you found one example of where that would be useful.
Right, yeah.
I mean, it could be in biology, it might exist.
Mm-hmm.
So, yeah, so, but industrially, I don't think anything that complicated has been thought about. So you're talking about like fluxing back and forth across the thing and doing a separation with kind of a fluxing operation.
Yeah, because like you could like have like something with like a lot of like you can have like some you have like more complicated things, like when you put it through one way it filters out one thing and then it filters out the other thing when you go back up through it.
Yeah.
Yeah. I'm not certain how that helps. You may
I can see how it might help. Can't think of where it would help, but
yeah.
I think if you figure out where it could help, that would be useful.
Yeah.
I mean, it could even be like a drug delivery thing or something too, like where you have when you punch in one thing and then it makes something happen that makes another thing, and then when you pull it back, it gets rid of that thing.
Okay. Yeah.
So there's probably some kind of biological process where that happens. There might be an industrial process too. It's almost like if you had a reaction, any chemical reaction that produces something of a different polarity or a different size, and then you wanted to kind of modulate that. I could see how someplace that could be of use.
Okay.
No one's done that.
Yeah.
Everyone is just like, it's almost like the land of idiots. The
Yeah.
main thing, you know what I mean? Like, but not necessarily. I mean, they're all good engineers, but basically, if you look at it, it isn't that complicated.
Right.
And it, like, even finding out one side's rough and one side's smooth took them 2 years. You know, and those are the pioneers of the field. You know, this is Thomas Edison of this thing. So it's kind of like makes you think like this could be a pretty easy place. It's like the big fish in the small pond thing, you know, that's a good place to be. So So anyway, and especially if there's a, dump trucks full of money, pouring money in all the time. So,
Right.
yeah, so it's kind of not a bad place to be. It's pretty easy to get a nature paper from this field. Put it that way. Like if you do anything like a little bit kind of interesting, like what you're saying, nature, no problem. Like, because so many people are interested in membranes. But I'm not saying to throw away your career, just to
Right.
chase after money and women, it's like basically, whatever you want to do.
Yeah.
But it sounds like a pretty good idea. I'd approve that proposal. It would need something where you said something tangible, like
Yeah.
one example. And then you could say like, but it could be obviously be used in all these other things,
Mhm.
and everyone go, yeah, that looks like it could be used in a lot of other things. But if you
Yeah.
kind of need one that says it, I think, but anyway, so this is that business, and then so that's like this absolutely the simplest thing you can say is like Purcell's law, and you just routinely just plop this equation and say I know the porosity of my film. I can say what the flux is going to be. I know what the pore size is because I did a SEM and I saw it, and then I know the viscosity of water, know the thickness of the film from the same SEM. It is all the parameters in here are from an SEM, one SEM of one film. Then you can just say, I know the flux. Then so this is kind of like the separation concept of like, so again, like, so there's an issue of like what happens in this tunnel. Like if the particles are hitting each other, then that's Brownian diffusion. If the particles are doing what they show here, that's Knudsen transport, right? Which is slower than the particles hitting each other. So if you're measuring pore sizes and then going across and then trying to find a dependence on pore size with the transport through it, you'll find out there's a transition point where you go from continuum to this kind of molecular scale transport through it. So this is just showing like the difference between this is a diffusion path through them. This is absolutely diffusion, like through that, and this is not. And then this is showing that if you can't absorb it, then you can't diffuse it. Like so if you're doing a separation, it's soluble to one, not the other, then you're going to get a good separation. So this is showing what can happen. So it isn't this idea of like it's squiggling through. Diffusion is the idea that it's moving through at such a slow rate that it's exploring the entire universe in here. So it can move in any direction once it's in here. That's Brownian motion. So it's going to go with time to the square root of time. Distance goes with square root of time. So, but if you have something like this, so this is a combination of being stuck in a hole and then ballistic motion. This is velocity. It's like transport is proportional to time. And then you get stuck in a hole. So it turns out when you do simulations of this, just like polymers and some gas molecule going through polymer, like for polyethylene, wrapping your food to keep the moisture out of your cornflakes. It's a typical example, right? So you want to have, so this is the kind of thing that actually happens. Get stuck in a little well region where the water can be happy, and then it suddenly randomly pops through a hole. So you can get a jump. So the motion is actually jump, stuck kind of thing. If you do 2D, you get this kind of picture of what's going on. So you can see like someone that was a pretty decent dynamic simulation guy decided to go after the dump truck of money and like do membrane stuff and like came up with this thing. So it's basically it's drawing the flies, the sugar is drawing the flies. Anyway, so if you want to look at the thermodynamic end of it, you can say like the flux is going to be due to a chemical potential difference. And then if you do that, then the chemical potential is free energy, which has a pressure term. So Gibbs free energy has a pressure term in it. If it's Helmholtz, it doesn't. But then also has like a activity part. In other words, like the chi parameter part. Activity coefficient times the molecular times the number of particles. So this is basically the concentration. So that's like the concentration gradient part, and this is the pressure part. So it has both. This would be transport through a porous membrane, and this is transport through a bulk membrane. So this is the idea, like if you want to be a membrane scientist, then you have to have an equation that governs all membranes, both porous and non-porous. So if you, turns out like the chemical potential will do that for you. Because it's got the porous number, the pressure gradient one, it's also got the concentration gradient one, Fick's law. So from that one equation, then you can get both Fick's law from it, and you can get also kind of Pucell's law from it, pressure gradient law from it. Okay, so that's like from the Bible, or whatever that book is. It's kind of like the Bible of membranes. It's trying to say like there is a universal law to all these membranes. Anyway, so and this just shows like that the chemical potential, the pressure would drive this one. So there's a pressure gradient, and here it's driven by concentration. Like the chemical potential is different on the two sides, pressure is the same. Unless you have pervaporation membrane. So if you have pervaporation, when you come through over here, it's a gas. Say you start with a gas and becomes a liquid over here. So then you have water condensing on the surface, and that evaporates. So you have a combination of diffusion through this and then evaporation here. So you have, in that case, for pervaporation membrane, which is used for separating you want to make non-alcoholic wine. So you have to get the alcohol out of the wine. So you put the wine over here. You have a membrane that allows alcohol through, but not water. And then the alcohol condenses over here, and then you evaporate it. That's a pervaporation technique to make, if you wondered how they made non-alcoholic wine. My wife just found a bottle, like one of these little bottles of non-alcoholic wine sitting somewhere. It had been there for like 13 years or something. It's like, oh, is it still good? But anyway, also for, let's see, removing, it's in the food industry, like pervaporation is popular, to remove water from stuff. Like if you had cheese or something, you need to get water out, I don't know, something. But so anyway, that's another kind of membrane separation. It has like, you have to have solubility, you have to have transport, and then you also have to evaporate over here. And if you want to know the flux through this, you have to combine all those three. Right. So it's like I said, there's so many different applications. You can kind of look at the look at that. What else we got here? That's kind of the same stuff. So the two things you'll see, and you'll see it in that paper, is selectivity and flux. So you want to have high flux, you want to get a lot of stuff through. So you want to get A out of the thing, like fresh water. And then you want to get rid of the B. So you want to get rid of the salt. Right. So you're going to have, like, if it's gases, it's like pressure A or concentration A, concentration B. So there's a selectivity number. You want that to be a huge number. In other words, 100 or 1,000. For an industrial membrane, you want it to be like above 50. Right. Then the flux has to be big to get your what you want to get out of it. And the flux is going to be this solubility and diffusion coefficient business, permeability, the size of the membrane, and make it thin. Right. And then the separation, kind of, the thinner it gets, the worse separation, the higher the pressure. So the bigger the flux, the worse the separation, is like a general rule. So there's a balance between the two to find the magic sweet spot for whatever you want. So you can see whenever the flux is big, you get a bad separation. Whenever the flux is small, you get a good separation. And there's some cases that deviate from that, but basically that's the game that all the membrane guys play. It's like trying to balance out these two. So you see in that paper, that's what he's doing. He's trying to get high flux and then better separation. Right. So whatever, this is like some industrial stream that produces hydrogen and also has nitrogen in it, and you want to get the hydrogen out. Because the nitrogen is kind of like a diluting your hydrogen. So that's kind of what, let's see what's I got here. Yeah, so this is just showing like so you make these membranes and you're going to end up with the solid layer, that's your separation layer, has defects in it. Then you have to engineer some way to plug the holes, like the Dutch guy sticking his thumb in the dam type thing. So somehow you're going to have to deal with a variety of kind of engineering problems with these. What is this showing? That's just showing the Knudsen effect of transport through a pore. That's nothing. So this is so you have, if you have diffusion and then you have or this shows the Knudsen effect pretty good. So you have the diffusion going through a material, and then this is the size of the material. So normally this N is 6, like 6 pi viscosity RH KT, right? So they're using molecular radius for RH. And then it's at a single temperature, so you just have 1 over this kind of N number, which should be 6. So it goes to 6. But as you get to below 5 angstrom, so if you're looking at these guys, you're like looking at all the gases you want to separate are below 5 angstrom. And all of a sudden this not 6 anymore, because you're getting into this Knudsen transport regime where you get this kind of, the pore gets so small that the particles don't hit each other. They kind of have effects to the pores on the transport. So the pores are making the transport wars through the thing. So you just model it differently. What else we got here? The diffusion coefficient versus sorption. Oh, this is just showing that there's also, this is a problem with, there's a problem in trying to balance selectivity and transport. And there's also a problem with trying to balance whether it absorbs the material or whether it transports. Right. So you want to have a high diffusion coefficient and you want to have like a high transport coefficient. So you want to get those things matched up. Like you want the top right corner, and different materials, depending on the gas you're using, the ability to transport and the ability to dissolve aren't necessarily compatible with each other. That's the point of that. And there's various trends, and so people have studied every possible trend. And these aren't necessarily, like, these don't necessarily make that much sense. Like log of molecular weight and diffusion coefficient. So diffusion coefficient should go with 1 over the size, and the size should go as a molecular weight to the 1/2, right? If it's a polymer thing. And then that means molecular weight to the -1/2. So diffusion coefficient versus log of molecular weight doesn't make any sense. Yet there's a trend. It's kind of linear, you know. It's kind of like, this doesn't make any sense at all. It should be log of diffusion coefficient goes with molecular weight to the -1/2. But it isn't, it's log of this versus that. So it's the opposite of what you would do if you were thinking. Anyway, so solubility increases with temperature. We kind of know that. That's an Arrhenius kind of behavior. I don't know, there's a bunch. This is 26, 110 slides on this thing. So we can't do it all. It's on the web page. So what we'll do is, like, there's too much stuff. So basically, it's a whole class, actually, if you want to do membranes. And there is another class, but it's ceramic membranes. But anyway, hopefully this gives you a little feel for what's going on with it. And then we'll do a paper. So the important thing is, like, what people, we'll just take a paper and like look at it in detail. Say, like, what are they saying about it? And then if we need to go back to this, we'll pick out the part we need from this. And then I think that's a better way to do this. Because you can't cover the entire membranes in like a couple days. I think. I mean, you could, but basically it would be a pretty rapid talking. You would retain like nothing from it. So anyway, so that's about it. So yeah, 2 papers, 2 days. Then you can take till like Friday of exam week to turn it in. I mean, earlier would be better, but basically, you know, kind of sometime on Friday. Because I think the grades are due on Wednesday or something next week. So it means I'm gonna have to speed grade. And I still have a pile to grade. Sorry, I kind of know exactly what's going on, but my brain shut down for a while. So, but I'll get to the grading. I keep going to it and it's like, oh no, I have to really go through each of these questions. I can't just like zip through this. And then it's like, it starts getting, I find something else to do. So I did review 2 papers this weekend. You know, it's like I'm always looking for something else. So anyway, I'll get to the grading. I think I'm 3 homeworks behind, plus the ones today. So it's like 3 or 4. It's like, yeah.
For the ones today, it says
do the first 5 simulations and then the 6th is optional,
Yeah,
but there's only 5 total.
oh, is
So
that right?
It's just because I
Well,
think,
there's like step 6 is the one that's optional, because you have to do
Yeah.
like the extra stuff.
Okay,
Because the first step is just installing Ubuntu, which honestly is an assignment in and of itself.
yeah,
Okay.
yeah, so that, yeah, the first one is installing it.
Okay.
Do a
But we don't
screenshot
have
of
it.
you sitting there or something, you know, like,
Yeah.
whatever that would be. Yeah.
Screenshot of Ubuntu open.
Yeah,
of the
So it's-
application.
yeah, so-
like,
yeah, so it's the 5th one, it's the last one, whatever, because I think that one you need to
Yeah.
compile it.
You need.
Yeah, you have to like
Illustrator
recompile it.
Yeah,
and-
yeah, recompile it, so if you want to do that, do it. If you don't, it's okay.
Yeah.
But I think generally, I did this in another class and everyone did that, you know. So it seems like maybe it's not that bad, once you get the installation of the entire thing, it's just one more step,
Yeah,
but anyway. Then I emailed the guy in Edinburgh, I said, I'm teaching this to grad students. And he was like, oh, I give that to undergrads. Of course, half the guys in here are undergrads, but basically. He thought it was like foolish, but he's in a physics department.
Yeah.
So I don't know to me, it's pretty challenging, you know. When I first did it, so I thought it could be beyond a grad student level. Basically, he was thinking like, this is so simple. He might have just been saying that to the British or the Scottish, I don't know. They're kind of funny, you know. Some of them are super nice, like 3/4 to 80%. And then there's this percentage that aren't at all, you know, and some of them are really, especially like you get closer to like Cambridge and stuff. Like I had a grad student email a guy at Cambridge, he came back and said, like insulted the grad student for asking him a question about his paper where he had made an error, you know. And it's like he was embarrassed that he had made an error, so his response was to insult the grad student who was like a meaningless person, you know. It's like, why, what kind of person is that, you know? So but generally, British are good, straight up, they're all pretty good. Much more congenial than Americans, I think, and stuff, so. But anyway, that's it, so.